Today we will see analysis of structures part 2, which is lecture number 6 in module 3 of engineering mechanics course. Today our topic of discussion will be to determine the internal forces that are developed in a member when it is subjected to some external force. In the preceding discussions, we have dealt with determining the external forces that occur in a member or the forces that occur in the joints in case of connected rigid bodies. In the preceding lectures, we saw some examples of connected rigid bodies like trusses, frames and machines, and we saw procedures to determine the forces that hold them together or the forces that occur in the joints. Today's interest will be to determine the internal forces that occur in a rigid body when external forces are applied. These forces are nothing but the interatomic or intermolecular forces that hold together the various parts of a member from deformation or failure when subjected to external loads. We have seen that in structures predominantly we have two force members and multi-force members. So, we will see how to determine the internal forces for the two force members and then the multi-force members. And the interest in determining these forces lies in analyzing the internal forces for predominantly two types of structures that we use in our civil construction or for other mechanical constructions. They are the beams, which are usually long, straight and prismatic members with supports and which carry loads, either distributed or concentrated loads. The other kind of structures are cables, which are used to tie say the electric poles or the cables that are used to carry winches. So, these members have predominantly the the tensile forces. So, we will see first how to determine the internal forces in a two force member. Let us consider first a straight two force member AB, which is subjected to the force F at A and an equal and opposite force at B. If we are interested to know what kind of forces are set up at a section say C, then let us create a virtual section at C and create the free body diagram of one of the portions, say AC. Let us draw the free body diagram of the portion AC. We have the external force F acting at A, and at C the various parts of these members develop internal forces that hold them together with the parts or portion of CB. So, these forces can be represented by these quantities. These are nothing but the various internal forces that hold the portion AC with the portion CB at this section C. These forces are the interatomic forces or intermolecular forces. Now, if we consider the equilibrium of this portion, that is the portion AC of this two force member, then for equilibrium to exist, the sum of all the forces should be 0 and sum of the moments has to be 0. And it becomes apparent that if we consider the axis of this member and if we sum all these forces at this section C, they have to be equal and opposite to this force, because this portion is again a two force member. So, we have the resultant of all these forces as F, which is equal and opposite to the applied force. Let us now consider a two force member which is not straight and try to determine the internal force that is developed in a non-straight two force member. So, here you see a member ABC which is bent, but it is a two force member because loads are applied at 2 points, at A and at C. We have these loads P that are being applied to this member. For equilibrium to exist, we know that these two forces has to be collinear. So, let us take a section D and draw the free body diagram of this portion AD. We consider this portion AD. We have the external force P that acts at A, and at D we have these internal forces that hold together this portion, that is AD, with the remaining portion DBC. For this portion AD to be in equilibrium, the sum of the forces and sum of the moments has to be 0. That means, the resultant of these forces should balance the force as well as the moment due to this force P. So, let us draw the resultant of these internal forces at D. At A we have the external force P, and at D the resultant of all these forces is equal to a force F and a moment M. How do we say that this is the resultant of these forces? If we consider this free body diagram, for the portion to be in equilibrium, the sum of these two forces has to be 0 and the moment of this force P about this point should be equal to this anti-clockwise moment m that we have marked at D. So, for a two force member which is not straight, the internal forces reduce to a force and a couple. This force F can be represented by its two components, one along the axis and one transverse to the axis. So, this represents the resultant of the internal forces at D for this two force member. We have designated the axial force and the transverse force as F and V and the moment as m. Let us now see how to determine these internal forces for a multi-force member. So, here we see a multi-force member A, B, C, D, and let us say we are interested to find the internal forces at this section J. So, let us consider the free body diagram of the portion dj, and we know that the resultant of all these internal forces will be a force and a couple, and that is the force is represented by its two components V, which is transverse to the section, and F, which is perpendicular to the section, and the moment is m. This force V tends to shear this member at this section J, and so it is known as the shearing force or the shear force, and this moment m tries to bend the member at this section, and so it is known as the bending moment, and this axial force F tends to compress or extend the member, and so it is an axial force either tensile or compressive in nature. Let us see how to determine this shear force and bending moment for a, let us say, a 3-dimensional structure or a 3-dimensional beam. Let us consider an arbitrary structure in space and consider a section say D in this member A, B. Let this member be subjected to some forces, say F1, F2 and maybe some moments M1 and so forth. For the equilibrium of this member, the internal forces that will be developed at this section D can be represented by all these forces. all these forces are 3-dimensional, they can have any orientation. So, let us consider this section. The resultant of all these forces at this section D, if let us say these are the local coordinates of this section, let me call this as small x, this as small y, and this as the z axis. So, the resultant of all these forces will be a force and a moment. So, these are the internal forces at this section D. If we take the components of this force, so we have a component along x, we have a component along y, and we have a component along z. So, let me designate these as Vy, Vx and Vz. The force Vx is along the instantaneous axis of this section, or which is perpendicular to this section, and thus causes a tensile or a compressive force on the member. These two forces, that is Vz and Vy, which lie in the plane of this section, tends to shear this structure in the plane Zy. The force Vz tends to shear the structure along the z direction, and the force Vy tends to shear the structure along the y direction. So, these forces are the shearing forces. Let us similarly consider the components of this moment. So, we will have a moment component mx, a moment component mz, and a moment component my along the x, y and z direction. This moment, that is mx, tends to twist the member at this section D. So, this is known as the twisting moment. This moment mz and the moment my along y and z directions, they tends to bend the member. So, the moment my bends the member in the plane x z, and the moment mz tends to bend the member in the y x plane. So, these two moments are the bending moments. So, we see that the resultant of the internal forces tend to twist, bend, or axially compress or extend or shear the member at any given section. So, knowing the behavior of these internal forces, it is possible to now design the member to resist these forces. The aim of design of various members of, let us say, the trusses or any machine or beams is to select suitable material and the cross sections that can resist these internal forces. With this understanding, let us move to analyze beams for the internal forces that are developed in them, and then we can move on to design beams, which obviously is not covered in this engineering mechanics, but later on in your second course you will be studying the design of beams or design of various other structures. Here you see in the accompanying picture what we call as beams that are used to support the roof of this structure. So, beams are generally long straight members which are used to support loads in the transverse direction. So, here you see this beam supporting the slender beams, and these slender beams in turn are supporting the roof of the structure. The loads, as you see, are perpendicular to the axis of the beam. Like for this big beam, you see that the forces from the slender beam are perpendicular to the axis, and also for these slender beams you see the load from the roof comes in the transverse direction. And we have already seen that if we have only loads in the transverse direction, they will cause only shear and bending, and they will not cause any axial force if it is a straight member. The loads could be either concentrated, as you see for this big beam, where the slender beams apply the load at these points, or it could be a distributed load like you see for these slender beams, where the roof planks apply continuous loading all along the member. The beams can be supported by various ways. Here you see a beam that is being supported by a roller and a pin, or a beam could be supported by embedding it into a wall like this picture as shown in this picture, or the beams could be overhanging, that means they extend beyond the support. In order that we are able to determine the internal forces, the supports should be statically determinate. So, let us see the kinds of supports that result in statically determinate reactions for beams. First, let us consider this simply supported beam. We have a pin connection at this end and a roller connection at this end, and if we draw the free body diagram of this beam as a complete structure. At A, since it is pinned, we have two components of reaction. Say if this point is A and this, let us call it as B, we have AY and AX, and at B we have a single component of reaction BY. And we know that for the equilibrium of this member, the sum of the forces and the moments have to be 0, and in plane this results in 3 equations from which we can determine the 3 unknowns, say AX, AY and BY. So, this combination of support is a statically determinate support reaction. Here we see what we call as cantilevered beams or beams which are embedded into walls at one of their ends. So, let us draw the free body diagram for this beam. Let us designate this point as A. At A, since all degrees of freedom are arrested, we have the two components of force AY and AX, and as well as there is a moment reaction. From the equilibrium of this member, we have 3 equations which can be used to determine these 3 unknowns, namely AY, AX and M. So, cantilevered beams are also statically determinate. This kind of support configuration leads to what we call as continuous beams. Let us designate this point as A, B and C. Here we see 2 beams are pinned at B, and this beam is supported BC, the beam BC is supported by a roller at C, and the beam AB is cantilevered at A, that means fixed at A. So, let us draw the free body diagram, and in order to develop the equilibrium equations, we have to dismember it as 2 members AB and BC, because we have already discussed that if we remove a structure from its supports, if it collapses, then we cannot consider the free body diagram of the complete structure. So, in this case, if we remove this structure ABC from its support, obviously it collapses. That means, the beam can rotate about this point B. So, we consider the free body diagram of the dismembered beam. So, first let us consider the beam AB, and at A, since it is fixed, we have the 2 components of reaction and the moment reaction, and at B, since it is pin connected, we have 2 joint forces, say By and Bx. Since the beam BC can rotate freely about this point B, there is no moment force at this joint. Let us consider the free body diagram of the beam BC. At B, we have an equal and opposite joint force as shown in the free body diagram of AB. So, we have these forces Bx and By, and at C, since the beam is supported by a roller, we have a vertical component of reaction, say Cy. Now, let us see how many unknowns we have. We have 3 unknowns at A and 2 unknowns at B, totaling to 5. And from this free body diagram, this Bx and By have already been accounted for in this free body diagram. They are only opposite in sign, so they do not constitute a new unknown, and we have one more unknown, that is Cy. So, we have a total of 6 unknowns to be determined. For the equilibrium of this rigid body AB and rigid body BC, from the equations we get to know 3 unknowns for each free body diagram, and since we have 2 free body diagrams, so we get 6 equations, and since the number of equation and number of unknowns are equal, the problem is statically determinate. Let us consider another example of a continuous beam. Here we have a beam ABC which is pinned at A, supported by a roller at some point between AB and at C. Again we see that if we dismember or if we remove this beam from its support, it collapses. So, we dismember and construct the free body diagram. Let us draw the free body diagram for the beam AB. At A we have 2 unknown reactions, AY and AX, and at the roller we have, let us say this point is D, we have a vertical component of reaction, and at B we have 2 joint forces, say By and Bx. For the next member, that is BC, we have these joint forces By and Bx, and at C we have the vertical component of the roller reaction. So, let us count the unknowns that we need to determine and see whether we have sufficient equations to determine. So, from this free body diagram we see that we have to determine 2 plus 1 plus 2, a total of 5 reactions, and from this free body diagram only Cy is the additional unknown, since Bx and By have already been taken care of. So, we have a total of 6 unknowns, and from the 2 free body diagrams we can write 6 equilibrium equations and all the 6 unknowns can be determined. So, this is also a statically determinate support reaction. Beams can be subjected to point or distributed loads as shown in these figures. So, here you see a point loading configuration like a force of P1 acting at B and a force of P2 acting at C, and here you can see a distributed load, either uniform distributed load or a varying distributed load acting on this beam ABC. For all these configurations, if we have statically determinate support reactions, we can determine them, and thus it is possible to proceed to determine the internal forces. So, the problem of beam design can be stated as that first we are interested in finding the internal forces that are caused because of the externally applied force. That is, we are interested to know the shearing forces and the bending moments. And once we have determined these internal forces, we now design the beam cross section and we select the beam material which can resist these forces under the applied load. Here you see some examples, like you see an I section beam which is made of aluminum. Here you see a hollow section beam, the material could be steel, or we have these wooden beams which are solid. So, in order to determine the shear force and bending moment, we consider the free body diagram of a portion of a beam and determine the unknown internal forces. So, let us see an example. Here you see a beam which is pinned at say A and has a roller support at B, and we are interested to find the shear force and bending moment at a section say C. We have some applied loads P and Q. So, first we determine the external reactions, and at B we have the vertical reaction By, and at A, since it is pinned, we have Ax and Ay. And we know that from the free body diagram and equilibrium equation, these three unknowns can be determined. Now, we consider a portion of the beam, that is section at C, either it could be the portion AC or the portion CB. Construct the free body diagram and determine these internal forces. So, here you see the free body diagram of the portion AC, and at section C we have the resultant of the internal forces having components V, which is the shear force transverse to the axis of the beam, and H, the axial force along the axis of the beam, and the moment M, which is the bending moment. And in the other free body diagram, that is the free body diagram of the portion CB, these forces are equal, but they are of opposite sense. Like here V is vertically upward, and then in the other free body diagram it is vertically downward. These directions that have been shown are taken as the positive convention, that is the shear force marked vertically upward on the left hand portion, that is AC, is taken as the positive shear force, and the axial force is taken positive along the positive direction of x. If we designate these local coordinates x, y and z perpendicular to the plane of paper, and the moment M, which is the counterclockwise moment, is taken as the positive bending moment. The positive convention has been chosen from their effects. We have seen already that the shear force V tends to shear a beam, and the direction of the force V tends to shear the beam in this fashion. And let us consider this bending moment M. This tends to bend the beam in this fashion, and the axial force H tends to pull this member, thereby the member is subjected to tension. So, these effects are taken for the positive conventions. Let us consider a simple example problem. Let us consider a beam AB with a roller support at A and a pin support at B and a concentrated load of 1000 newtons at C, and say a point moment of 500 Newton meter. The various dimensions all dimensions are in meters. Let us say we are interested in finding the shear force at a distance x from the end A. How do we proceed? We first construct the free body diagram of the complete beam to determine the external reactions. So, let us draw the free body diagram. At A, we have a roller support. So, we have one component of unknown reaction, and at B, we have two components of unknown reaction, and we have the applied loads 1000 Newton and a point moment of 500 Newton meter at C and D. Now, from this free body diagram, we can write three equations which can be used to determine the three unknowns. So, let us write those equations. We can write the force summation equation for the vertical component. So, we have the force Ay, the force By, the two unknown vertical reactions, and the vertically applied load which is downwards equal to 0. Now, let us write a moment summation equation about A. We have the 1000 Newton force having a clockwise moment about A. So, which is a negative moment. So, we have minus 1000 into 10, which is the moment arm. At D, we have a clockwise moment of 500 Newton meter. So, which is also a negative moment, and at B we have two unknown reactions, that is Bx and By. The moment of Bx is 0 because it passes through A, but the moment of By is counterclockwise. So, which is positive, and the moment arm is 40 meters. So, we have plus By times 40 equal to 0. And let us write the force summation for the x axis. We have only one horizontal component of the force, that is Bx, and so it has to be 0. So, from these three equations we can determine the three unknowns, that is Ay, Bx and By. We have already found that Bx is 0. By solving 1 and 2, we find By to be 262.5 newtons and Ay as 737.5 newtons. Now, we can proceed to determine the internal forces, that is the shear force and bending moment. To determine the shear force and bending moment at this section C, or a section at a distance x from A, we consider the free body diagram of the section, which is at x meters from A. We have the applied load of 1000 Newton at C and the reaction Ay, which has been found to be 737.5 Newton. The resultant of the internal forces at this section will be the shear force. We can see that since there is no horizontal forces, the axial force is 0. Even if you will consider the axial force from the free body diagram, it will turn to be 0, and we consider the moment m. Both have been taken in the positive sense as discussed. Now, from this free body diagram, let us write the equations. First, let us write the force summation equation, which gives that V plus Ay should be 0, because we have the vertical component of the force V and the vertical reaction Ay. Now, let us take the moment summation about this point, that is a point on this section. Why we would like to take it? We can take it about any point, but since V is an unknown, we can avoid it in the moment equation if we take the moment summation about a point on that section of our interest. So, let us take the moment and equate it to 0. So, that states we have this force Ay, which causes a clockwise moment at this section. The moment arm is x meters. So, we have Ay times x, which is a negative moment because this is a clockwise moment about this section, and we have the moment of this 1000 Newton force, which will be counterclockwise about this point. So, we have plus 1000 times the moment arm will be x minus 10 meters, because this force of 1000 Newton is being applied at 10 meters from this end A. So, we have the moment arm as x minus 10 and we have this moment m, which is a positive moment. Since we have already determined Ay, now we can find V as well as this m, and these two are the internal forces at this section. Similarly, we can consider any section along this beam and determine the shear force and bending moment at that section. Let us consider another example. Here we have a curved beam which is supported by a pin at say B and at A by a roller. This is a circular beam with radius equal to say 6 meters. There is a concentrated load of 100 newtons applied at the mid section of this circular arc beam. Let us say we are interested to find the shear force and bending moment that occur in this beam as a function of theta, where the theta is taken from the point A towards the point B. So, we are interested to find V, the shear force and bending moment as a function of theta. So, how do we proceed? We first determine the external reactions and then we construct free body diagrams for portions of the beam and develop the equation. So, first let us consider the free body diagram of this complete beam. So, at A we have a roller support and at B we have a pin support and we have an externally applied load of 100 newtons. The radius is 6 meters. So, let us write the equations resulting from this free body diagram. If we sum the horizontal component of the forces, we find that we have only one horizontal force and that is Bx and it becomes 0. Let us take the force summation along y axis. We have this reaction By and the reaction Ay plus the externally applied force 100 newtons along the y direction. So, we have Ay plus By minus 100, the downward force equal to 0. Let us take a moment equation, and it is convenient to take the equation about B. Then we will be able to find this reaction AY and equate it to 0. So, the moment arm of this reaction AY is 6 meters, and this causes a clockwise moment about B. So, we have minus AY times 6, which is the moment arm. The 100 Newton force has a counterclockwise moment about B, so which is positive. So, we have plus 100 times the moment arm of this is, this load is applied at a radial angle of 45 degrees. So, we have the moment arm as 6 cos 45. So, from these two equations we can find AY and BY. Now, after we have found these external reactions, we can move on to determine the internal forces. So, let us consider a portion of the beam before the mid section. Let me call this as C and O. So, we are considering a section of this beam before the mid section C. So, at A we have the external reaction, and we have the shear force V transfers to the member, the axial force say H, and the moment M. So, this V, H and M are the resultant of the internal forces at this section. V is radial and H is along the tangent of the axis of the beam, because this is a circular arc, and M is the moment of all these internal forces. Now, from this free body diagram, let us write the equilibrium equations. If we sum the forces along the x direction, we have, these are the positive x and y directions, we have the component of this shear force in the negative x direction, which is minus V cos of theta, and we have the horizontal component of this axial force H, which is H sin theta, and this has to be 0. Now, summing the vertical components, we have V sin theta, which is positive, plus H cos theta, which is the component of this force in the vertical direction, plus AY equal to 0. Let us take the moment summation about, say, this point O, because this V, the shear force is radial and passes through this point O, and it can be avoided in the equation, and is minus A y times 6, the clockwise moment of this reaction A, minus H times 6, because this force H is tangential at this point to this radial line. So, the moment arm of this force H is 6 meters again. This plus the moment m has to be 0. From these equations, we can find the three unknowns, that is V, H and m. Now, we can consider the free body diagram of a portion between C and B, and we can write the equations for shear force and axial force and bending moment. And now we have the shear force, axial force and bending moment as a function of theta as interested by us. We will continue with our discussions on determining the shear force and bending moment in beams in the next lecture.